Let's go.
God, I'm having such a hard time hearing you. So I feel like you just did a handoff. So I guess we'll go ahead and get started. Hello, everyone. My name is Mya. I'm here today to talk to you about how to deploy and manage your gRPC services on top of Kubernetes. I know everybody's got opinions about resume slides, but during the day, I'm a principal engineer working at Indeed.com. Outside of that, I'm a mother of one. I have a couple dogs, plenty of hobbies, and I contribute to open source a lot. One of my biggest personal projects is working on a system to kind of identify how project repositories depend and consume one another. Much of what I cover in the presentation today stems from what I've learned working both on my side projects as well as my full-time job. And I'm on social media everywhere, so you can feel free to reach out and connect, go from there. In today's talk, I'm going to spend most of it in a code editor and just kind of interactively walking through the project. But I will kind of stop and give a little bit of background, provide a high-level overview of a system that we'll be working with. And then even once you're kind of in the editor, you'll notice I also try to include a lot of supporting context or documents along the way. So, and then finally, we'll wrap things up with a little bit of Q&A. So first off, gRPC is an open source remote procedure call framework from Google. It's built on top of protocol buffers, a tool that allows services to be defined in a language agnostic way. As a result, this makes the framework really versatile and able to support many different languages. It's because of this that I've actually been working with it over the last 3 years across Golang, JavaScript, Node, and Java. In this talk, I'm not going to dive into the depths or specific details about gRPC. Rather, I'm going to focus on how to kind of configure some of its features and run it within an orchestrated environment like Kubernetes. Specifically, we're going to be looking at things like health checking and client-side load balancing, how to pick kind of the right service for the right job. If you want to look up for more information on gRPC, I definitely suggest checking out their website. Next up is Kubernetes, and God, I really wish I didn't have to kind of do the whole intro here, but for those that are unfamiliar, it is robust container orchestration platform. It kind of provides a lot of the essential building blocks for developing and deploying containerized workloads. I know there's a lot of components within the Kubernetes ecosystem, so it's definitely a little overwhelming to get started. I'm not going to be able to cover every element today, but I do try to, again, kind of provide documentation, link out to further context for folks where necessary. The test system that we have is pretty easy. I know this diagram's a lot to digest, but there's really two main code components. There's the client that will just kind of issue requests against the server, and our server-side component, which will just echo back the host name of the server instance. And then using configuration, we're able to kind of deploy a single version of the server, and then deploy 3 distinct versions of our client application. Now that we kind of have a sense for the system at large, we're going to be, we'll shift over and kind of walk through the code repository. For those that are interested in kind of following along at home, all of this is available on GitHub at that address. So again, the address for those that are interested. The first thing you'll probably notice on here is I do provide instructions on how you can kind of do this at home using a simple little kind server, and then kind of walking through each of the YAMLs. I do link to kind of the presentation outline that we're roughly going to follow today. It includes everything about kind of the current cluster setup to some things to kind of keep an eye on as we move through it. First, we are using a DigitalOcean hosted cluster. I picked DigitalOcean for a few reasons. One, really easy to get started with, but two, they have support for HTTP2 on, or at least gRPC on their load balancers, which was a really valuable play for some of the work that's being demonstrated here. And then I'm using a modern version of Kubernetes. I say 1.16. And I do often work with 1.17, but really just looking for something that's able to support the latest versions of the YAML. So some key principles to keep in mind as we go throughout this presentation. Even if you're not working with Go or anything like that, the features that I'm trying to show are available in most of the languages today. And what's kind of even nicer when working across kind of the Golang or the gRPC projects is I noticed that a lot of the features actually are implemented in very similar ways as well. So you can kind of see elements between each of the libraries that kind of stand out. With gRPC, kind of your first entry point into your project is your proto definition. It's where you define the messages that are kind of representing your requests and your responses. It's where you write down kind of the service contract and the various operations that you can perform against that given instance. These can be unary in the sense that for every request that you issue, you get one response. Or they can be stream-based calls, whether that's a server-side streaming event or a client-side streaming event, or even BiDi for chat-heavy systems. Any changes to this file go through the proto-C compiler. For simplicity, I use a Go generate syntax, but you could just take this proto-C line and kind of drop it into shell and invoke it directly. This will end up producing a single file with kind of all the generated messages that you defined, as well as kind of some server and client interfaces. So demo client, which is something you'll see later on. Next up is really kind of taking a look at the server model. So like I said, one of the things that code generation gives you is both a client and a server interface to adhere to. You can implement that server interface, and here I'm just providing a simple little echo function that kicks back the host name. Earlier in the code, you can kind of see where we're starting up the server. We can register any number of desired application or a desired gRPC servers with the instance. You can't register multiple of the same service, so I couldn't do 2 instances of register demo service. But you could register, demo service, and then where I'm doing here, where I'm registering the health service as well. So gRPC does provide a few services out of box. One is reflection and one is health. The health server is really useful because it allows you to have your clients transparently check backend serving status. And if a server is unable to service traffic, clients are smart enough to be able to pull those instances out of rotation and then kind of prefer instances with a healthy serving status. To do this, you just have to start up a new server, register it, and then spin up a background thread that can kind of go and inspect your system dependencies and then toggle serving status appropriately. Next up on the list is the client. This is actually a lot more involved. I'll come back up to the import here, but the first thing I wanted to call out was the service config, which is used to configure a lot of the communication elements of kind of gRPC clients talking to the server, specifically things like load balancing policy and the health check configs. By default, gRPC uses a pick first strategy. You can see I'm overriding it to be a round robin approach here. That is, any server instance that's returned will actually be serving traffic. The health check config allows you to specify the health check service name. Empty string tends to default to the global status of the service. So here's kind of where we're initializing a lot of that health check operations. By providing the health check config, there's kind of some plumbing that happens under the hood, where you then also need to make sure that you import that health package so that way the client probe gets initialized properly. This is likely a Go specific thing, but it was something that I thought was really kind of dug into the documentation. And the next element for the client is really a target address that it's going to dial. So this follows kind of a fully qualified URI syntax. The structure is here. Some good examples. We're going to primarily work with the kubedns one inside of the demonstration today. But there's other ones out there. You can use console, you name it. I don't think this one's packaged out of box, but I know people that have implemented them. And then if you wanted more information about how kind of name resolution works, you can kind of go dig into it a little bit more there. But generally, that's how it works. We're going to let clients kind of pass in the targets they're dialing. We're going to use insecure communication just because it's a demo. And then you see that it kind of just loops pinging the server to get information. So we talked a little bit about load balancing health, the gRPC targets. The Docker file is probably the next good step. I'm going to ignore some of the build stuff for now, but it's probably worth noting that the one thing that I did pull in was a health probe. The health probe is going to allow you to kind of poke and prod the service, inspect its health serving status, and determine if it should be kind of available in Kubernetes. We'll get down to the manifests later that kind of enable this capability, but having this binary on the image is important. And then Gawk, which is just the binary that's compiled from the source code that's here, short for gRPC on Kubernetes. And kind of one last little bit, which we end up specifying a non-root user and group, just to kind of get around some of the issues that you see when running on Kubernetes with strict pod security policies enabled. If your container runs as root, it will likely not start up. So that's really it for the application kind of level of things. We're going to kind of get into more of the Kubernetes specifics now. The first thing up is a namespace, which allows you to kind of have a single isolated unit of work inside of Kubernetes. They call them mini virtual clusters. I look at them as little resource containers. So I just created the gRPC namespace. I already have some of this stuff already set up, but we'll get the watch going at least. So there's nothing there. Once the namespace is set up, we can start sending components into that namespace, primarily the workloads that we want to see running. So Kubernetes workloads comes in many different shapes and sizes. I'm not going to walk through probably all of these today. The one that we are using, and you'll most likely end up using in a lot of your projects, is deployments. It's just a generic mechanism that lets you attach kind of rollout strategy to replica sets. So if we apply the server deployment, we'll see that the server instance gets applied and that one instance starts to come up. What's happening here is that even though we detect that it's running, the health probe is waiting for the server to actually set its serving status to ready. And then once the server is actually ready and starting to service traffic, does Kubernetes actually detect that it's able to do that. This is done because we set the liveness and readiness probes on our deployment. This really just says, go execute this binary. Here's the address to point it to. You can optionally specify a service address. But each of these mean two different things. Liveness probes primarily when to detect an application degrades into broken states and can't recover except by restarting. And then readiness probes are used to kind of determine when it shows up in DNS records for kubedns. That is, that it can actually service and process traffic. We set the desired number of replicas to 1 for now. That was primarily because we can now walk through a quick little scale event. One server is probably fine for the sake of this demo, but let's kind of get 3 instances going because we really want to show that traffic is able to route between all backend instances, not just one backend instance. So you can see that the other 2 are slowly coming up, finally completely rolled out. And so we have servers to be able to process workloads. that's not usually enough. We want to be able to actually make use of them. Before we can actually deploy any of our client code, we need to attach some services to it. Services is kind of Kubernetes generic language for how you kind of glue the various systems together. Most of these mechanisms result in some kind of DNS record. Cluster IP creates an A record inside of kubedns. Node ports kind of build on top of the existing cluster IP semantic by exposing the service outside the cluster with a common port on every node of it. Load balancers build on top of that, but are primarily provided by your external cloud provider. And then headless services, which actually strip out the cluster IP and expose the pod IPs directly to their clients. We'll kind of get into each of these a little bit more later on. But this is kind of just a quick dump of all the different options that you really have in Kube. So quick little look at the cluster IP, the headless. So difference here, really just setting cluster IP to none versus type equals cluster IP. And then load balancer, just setting it to type load balancer. I use distinct name addresses to be able to make sure that each of them were resolvable and easily targetable. So we'll go ahead and quickly apply that. And then we should see these come up. The load balancer will take a minute or so to provision. We're waiting on DigitalOcean to kind of go and provide us with that stable IP, but we've got other things we can do in the meantime. Let's go ahead and start making some use of the cluster IP service. So the way cluster IP works is clients will do kind of an NS lookup for the service that, whatever your target name is. In this case, it will be something like server cluster IP dot whatever the namespace is. DNS will return back a service cider IP, which is 10. In my case, I'm using 10.43, but it's whatever your cluster is actually configured to. In the example here, DigitalOcean looks like they use 10.25 or 245. That cluster IP will route to the kube proxy instance, which then ends up routing to one of the 10.42 addresses in the background. This is great because it lets you make use of things like topology-aware network routing, but kind of the one downside is that gRPC sees a single address, and so it only establishes a single connection to its backend. So the way that this ends up manifesting, if we apply this, we'll watch that roll out in a minute, and then start tailing some logs. You'll see that the server, only one instance or one server is really handling traffic at this point. The cluster IP does give you failover type capabilities. So if we went and deleted that pod, you can see that the traffic shifts from one instance to another. And we can, again, do that and watch the same thing happen where traffic shifts from one instance to the next. So it does give you some failover, but it doesn't distribute load across the backend. Some of this kind of comes from the way that kube proxy is configured. By default, it's usually configured with IP tables. You can configure it using IPVS to get load balancing support, but there's much more detail on this kind of in the attached blog post. But that's it really for cluster IPs. The next one on our list is the headless service. And the way that the headless service works, which is great, is if you look up an address, you're more or less returned the IPs of the pods. That removes the 10.43 encapsulation, and it lets gRPC establish a connection for each backend server instance and route traffic across each of them appropriately. This is kind of great because this gives you the distribution of workload that you're looking for. Oh, excuse me. But it doesn't respect topology-aware networking. And so what that means is when you do that NS lookup, you're always going to get back the full list of pods rather than the ones that are just on your host or the ones that are just on your node, so on and so forth. So we just deployed the headless address. If we actually go and tail those logs now, we actually see that every instance of our backend is handling traffic. Another disadvantage to this approach is that the DNS lookup is cached. And so if we scale our server instances down to 2, we'll notice that it respects that and it starts to send all of its traffic to 2 instances. But if we were to ever scale this back up to 4, there's a long lead time from the point where that scaling event happens to the point where the actual client realizes there are new addresses available. So we're still waiting on a couple instances to get healthy. So 3 are ready now, which should mean the client should pick up on it, but we still see that only 2 instances are handling traffic. So something to be mindful of as you use headless services, but they do provide a lot of great value. So the last one that I wanted to cover was the load balancer IP. And at this point, you can see that an external IP has been provisioned for us. Load balancers are a little interesting, primarily because it requires an external cloud provider to do the provisioning of the load balancer for you. But what's nice is that it gives you a great way to kind of expose services outside the cluster. So here, what we're going to do is configure our client pod to communicate with the load balancer. That load balancer will then route between all of the physical nodes within your cluster, which will then use the underlying proxy mode, whether that's IP tables or IPVS, to route between your backend server pods. So it's just going more or less host network to then the service cider range here. So like I said, this is great because it lets you expose services outside of the cluster. We'll quickly go and grab the provision load balancer's IP address. And then we'll go and apply that to the cluster. So we'll be creating now a load balanced client. That load balanced client's already up and running. Like the last one, we can go and tail its logs. Similar to the cluster IP, you do see the sticky sessions with your backend instances, again, kind of citing the behavior with IP tables here. And then similarly, it does handle that failover in traffic from one instance to another. And yeah, the thing to be aware of is that this does have some user visible impact in that clients may end up seeing, an RPC error here or there, depending on when that disconnect happens. If it happens when no requests are being issued, it's not going to impact them, but just something to be aware of. But that's all I have for y'all today. Thank you.
All right, let's see if my sound is better now, or is it still crappy? I think my sound. Billy, can you jump on, please?
Hey, can you hear me?
Yeah, I can hear you.
Oh, great. Awesome.
So my sound's kind of crappy, I believe.
No, it's good.
Maya has...
It sounds good.
Oh, right.
Weird. It must be on my end then.
Well, anyway, I want to thank you for your presentation. At this point, I do not have any questions.